Okay, so let's continue in Chapter 7 on functions. In this video, we're going to talk about some special types of functions called injective, surjective, and bijective functions. It might not be so clear why we care about these things right now, but later in Chapter 8, these things are going to be extremely important. So you've got to try to get these definitions under control. Okay, so the first definition. So we say that a function f from a set A to set B is injective if any two different elements of A have different images. Okay. In other words, a function is injective if whenever x is not equal to y, that logically implies that f of x is not equal to f of y. So this is of course for x and y in A. So in other words, yeah, so like this says, if x is not the same as y, then f of x is different from f of y. The contrapositive of this, of course, is that f of x equals f of y logically implies that x equals y. Maybe I'll move this x, y, and A above. Okay, so a function is injective if different elements of A have a different image under f. So in other words, if x is not equal to y, then f of x is not equal to f of y. Or the contrapositive, if f of x equals f of y, then x equals y. Another terminology for this is, so we sometimes say, instead of injective, one-to-one. So if I say that a function is one-to-one, that means the same thing as injective. Okay. And alternatively, we sometimes use the word injection. So, if we might say f is an injection, that just means that it is injective, right? So all these things mean the same thing. F is injective, f is one-to-one, or f is an injection. Yeah, it all means the same thing. Okay, let's look at an example. So for instance, suppose I let f be the function from the reals to the reals defined by f of x equals 2x plus 5. Okay, so if you look at the function, if you plot it, it's a straight line, right? It's a straight line where the y-asymptote is 5 and the slope is 2. So it's kind of a somewhat steep line. Okay. So I claim that f is injective. So I want to say that any two different real numbers have different images under f. Or in other words, if two numbers have the same image under f, then they must be the same number. To prove this, I want to go back on the previous slide to this definition, or this statement here. So we said that a function is injective if it holds that whenever f of x equals f of y, then x equals y. In a lot of cases, this is the easiest way to show that something's injective. So in this case, what I would do is, so here I'm claiming f is injective. Here's the proof. So let x and y be real numbers. In other words, let x and y be in the domain of f, right? The real numbers. And suppose that f of x equals f of y. And we want to deduce that x is equal to y. And in this case, it's going to be pretty easy, right? Because you can take, so if f of x equals f of y, that implies that 2x plus 5 equals 2y plus 5. Now, if I subtract 5 from both sides, that means that 2x equals 2y. And now if I divide by 2, I get that x equals y. So what I've demonstrated is that whenever f of x equals f of y, x must equal y. Okay, so that actually proves that this function f is injective. Okay, let's look at an example of a non-injective function. So let's take, for example, so let f be the function from, again, from the reals to the reals defined by f of x equals x plus 4 squared. Now, I'm going to show that this is not injective, but, you know, you should be able to kind of recognize when a function is injective or not. One way to recognize that, if you have a function like this where you can plot it pretty easily. So if I plot this function, we've got that at -4 it's 0, and it's a kind of quadratic function. It has only one root at -4, so it kind of goes like this, right? It's a parabola. How do I know that this is not injective? Well, the point is that if I take, the question of whether a function is injective is, are there two different values which have the same output? And here we can clearly see that there are, because if I take a sort of horizontal line here, it cuts through the function twice. So if I kind of take this to be my x and this to be my y, then definitely, so f of x is equal to f of y. Now, I want to clarify that this is a picture. This is not a proof, because in particular, I haven't proven that the function even looks like this, although we sort of know that it does. To really prove that this is not injective, what we need to do is give a counterexample. So I'm claiming that f is not injective, or maybe I'll use the other terminology, f is not one-to-one. Okay, so my proof is by taking a counterexample. So for example, suppose we take x equals -5 and y equals -3. And I've chosen that kind of carefully, or specifically, so that I know that the f value at these numbers will be the same. I chose them to be on opposite sides of the number -4 over here. So just like in the picture. So if I take f of x, that's -5 plus 4 squared, which is -1 squared, which is 1. And if I take f of y, I get -3 plus 4 squared, which is 1 squared, which is 1. So f of x equals f of y, but x is not equal to y, so it's not injective. Okay. Or in other words, it's not one-to-one, right? Remember, one-to-one and injective mean the same thing. Okay, let's look at another example. So suppose I take the function, f from 0 to infinity, the interval 0 to infinity, to the interval 1 to infinity. So by the way, I'm not sure whether I've ever introduced this interval notation, but generally speaking, if I have the interval a,b, that's the set of all x and r, such that x is between a and b, strictly between them, so not equal to a or b. If you take some square brackets, that means x and r, such that x is between a and b and might be equal to them. If you take partially square brackets, that means a similar thing. So and maybe for completeness, I'll draw the last one. So if I take this, it means this. So x is greater than a and less than or equal to b. Okay, basically when I draw these intervals, it means all the numbers between a and b, where if there's a square interval on one side, it allows you to be equal to that number. And if there's a round bracket, then you have to be strictly greater or strictly less than that number. When you do that with infinity, so if I write, say, 0 to infinity, or generally if I write a to infinity, that's the set of all real numbers such that x is bigger than a and less than infinity. Or in other words, every real number is less than infinity, so you can just write that x is bigger than a. By the way, never write this. Something like, I don't know, a to infinity, including infinity, right? So this part doesn't make any sense, right? Because infinity is not a real number. So you can't include infinity in your set. Okay, so back to the example. So let f be the function from this set to this set such that f of x is 1 plus 1 over x. So I claim that it is injective. So suppose f of x equals f of y for some x and y in the domain of f, so between 0 and infinity. Then what we get is that 1 plus 1 over x equals 1 plus 1 over y, which if we subtract 1 from both sides means that 1 over x equals 1 over y, which implies that if I multiply both sides by y and multiply both sides by x, I get that y is equal to x. And so f of x equals f of y logically implies that x equals y, so therefore it's injective. Now, one thing that's worth mentioning is that if you have a function that's not injective, you can sometimes turn it into an injective function by restricting the domain. So if we go back to this example here, remember this parabola, this quadratic function, x plus 4 squared, is not injective when the domain is the set of all real numbers, right? So when the domain is a set of all real numbers, you can plug in -5 and -3, and they both give you the same f value, so it's not injective. However, if you look at this picture, if I was to kind of keep this half of the graph over here, but somehow delete this half of the graph, then it would be injective. So if I took f from, with the domain being -4 to infinity to r, such that f of x is equal to x plus 4 squared, then this is injective. Because you no longer have two different values that have the same output. Let's actually do this as an example. So in case this description wasn't clear. So let f be the function from -4 to infinity to, let's say just to the reals, be defined by f of x equals x plus 4 squared. So I claim that f is injective. So even though it looks like the same function we had before, and before we said that this wasn't injective, now that I've changed the domain, it will be injective. Okay, so let's suppose, so the way that these injectivity proofs usually work, if you're trying to show something is injective, let's suppose that x and y are in the domain, so they're between -4 and infinity, and that f of x equals f of y. So this means that x plus 4 squared is equal to y plus 4 squared. Okay. Now the way that these things work is that if something squared is equal to something squared, that implies that the absolute value of that thing, so the absolute value of x plus 4 is equal to the absolute value of y plus 4. Now here's where the domain comes in. So everything I've written so far would have been true even if I had the domain being all real numbers, like we had before when it wasn't injective. But now the difference is, now that the domain is only numbers which are at least as big as -4, we can say that since x plus 4, or sorry, x is at least -4, we know that x plus 4 is at least 0. So the absolute value of x plus 4 is just equal to x plus 4. That's how absolute values work, right? Similarly, y is at least -4, so absolute value of y plus 4 is equal to y plus 4. So therefore, since we've already proven that the absolute value of x plus 4 equals the absolute value of y plus 4, and we've proven that absolute value of x plus 4 is just x plus 4, and absolute value of y plus 4 is y plus 4, we can put this all together to get that x plus 4 equals y plus 4. Therefore, by subtracting 4 from both sides, we get that x is equal to y. Okay, so this function is injective. So this is a bit of a lesson to you that if you're trying to check if a function is injective, the domain is very important. Okay, so now we're going to look at the next definition, which is surjectivity. Definition: a function f from a to b is surjective if for every y in b there exists x in a such that f of x is equal to y. Okay. So in other words, a function is surjective if the range of f is equal to the codomain of f. Okay, another terminology for this is either that we sometimes say f is onto, so onto means the same as surjective, or that f is a surjection. So if you ever hear the word onto, that means the same as surjective, or if somebody says that a function is a surjection, that also means the same as that the function is surjective or onto. Or the same thing as saying that the codomain of f is equal to the range of f. So if you forgot these words like codomain and range, I suggest reviewing them from the previous video. Okay, so let's look at one of these examples again, but this time from the perspective of surjectivity. So suppose I let f be a function from the reals to the reals be defined by f of x equals 2x plus 5. So I claim that this is surjective. So to prove this, what we need to do is show that every element of the real numbers, which is the codomain of this function, so every element of the codomain can be written as f of something in the domain. Or in other words, we want to show that everything in the reals is in the range of f. So let y be any real number, and we want to show that it's in the range of f, so we want to find some x such that f of x equals y. Now, it's pretty easy to figure out how to do that. I mean, so this is a kind of side calculation. So if I wanted to have f of x equals y, what I would want is to find an x such that 2x plus 5 equals y. So if I solve for x, that tells me that x is y minus 5 over 2. Okay. So this gives me some idea of which x I should pick. So let x be equal to y minus 5 over 2. So then f of x is equal to 2x plus 5, which is 2 times y minus 5 over 2 plus 5, which, unsurprisingly, since I set it up like this, is equal to y. Okay, if you do the algebra, you'll see that this simplifies to y. So therefore, y is in the range of f, and so this is true for every real number y, so therefore f is surjective. Okay, now when you're talking about surjectivity, your domain and your range are going to be really important. So as an example, just a small tweak of that example from the previous slide can give you a function that's not surjective. So for example, if I change the domain and codomain to be the integers, so let f be the function from the integers to the integers defined by f of x equals 2x plus 5, you might think, okay, this should be surjective too, because 2x plus 5 was surjective on the previous slide when we went from R to R, so why shouldn't it be surjective now? But it's not surjective, okay? Because, for example, so this is, so like I said, it's not surjective. And the reason is that you can't actually get every integer by applying f to some integer. So it's not the case that every number is in the range of f. So for example, a key thing here is that for any, let's say x in the integers, if I take f of x So that's going to be 2 times x plus 5. This is always going to be odd because it's 2 times a number plus 5. Okay, that has to always be odd. So in particular, the number 2 is not in the range of f because there doesn't exist x in the integers such that f of x is 2. Okay, so this is just trying to illustrate the fact that the domain and the codomain are really important when you're dealing with surjectivity. Okay, let's consider another example. So suppose that f maps the reals to the reals such that f of x is x plus 1 squared minus 1. So maybe think for yourself, is this onto? Is f onto? So onto means the same as surjective, remember? Well, let's think about plotting this for a second. So, I'm not going to plot this really precisely, but basically like the minimum point of this parabola is at -1, and the minimum will be -1. So it's some kind of a parabola like this, right? That's probably horrible. When I plug in 0, it should be 0. So maybe I'll draw it a little bit more accurately, and maybe it looks something like this. Okay, I think this is still terrible, but whatever. Okay, so is this onto? Well, I think it's clearly not onto, right? Because, how am I, you can see the minimum point is at -1. So it's impossible, for example, to plug in a value and get -2. So the answer is going to be no here because there does not exist x in the real numbers such that f of x is equal to -2. So therefore, -2 is an element of the codomain, which is not in the range, so it's impossible. Now, I haven't really justified this. So, and you should always remember, you need to justify things properly. So here's a proof of this fact. So suppose that x is in R and x plus 1 squared minus 1 is equal to -2. So then x plus 1 squared is negative. So if I add 1 to both sides, I get x plus 1 squared is -1, but the square of a real number is always at least 0. So this is a contradiction. So one sort of symbol for contradiction is 2 arrows pointing at each other. So that's what I'm using here to say this is a contradiction. Okay, so this function is not surjective. However, notice that if I was to change the function a little bit by changing its codomain, you would get a surjective function, right? So if I was to modify this by changing this r here to the interval -1 to infinity, then this would be surjective. Okay, so again, the domain and the codomain are important for understanding if a function is surjective. Okay, now let's add another definition, which is going to be basically just the combination of the previous two definitions. So definition, a function f from a to b is a bijection if it is an injection and a surjection. So we also say, so kind of other terminology, we could say that f is bijective or f is a one-to-one correspondence. I don't love this terminology because it kind of sounds so similar to being one-to-one. So remember, a function is one-to-one if it's an injection or injective, but this is saying it's a one-to-one correspondence if it's bijective. Okay, so it's important to keep that clear. One-to-one is not the same as being a one-to-one correspondence, right? One-to-one correspondence means that you're injective and surjective, but just saying it's one-to-one just means injective. Now, one of the important things about bijections, which is going to come up a lot in chapter 8, is that having a bijection between two sets allows you to kind of compare the sizes of those sets. So to think about this, so let's think of a sort of example. So suppose that F from the set 1, 2, 3, 4 to the set B is a bijection. My question is now, how large is B? Okay, or in other words, how big is the cardinality of B? And if you think about that for a little while, you'll see that the answer is it's going to have to be 4, right? Because, for example, okay, F1, if I look at F of 1, F of 2, F of 3, and F of 4, those are 4 distinct elements of B because F is injective. So F doesn't map 1 and 2 to the same value, right? Or to the same element of B. It doesn't map 1 and 3 to the same element. You know, it doesn't map any two different numbers to the same element. So F of 1, F of 2, F of 3, and F of 4 are all different. So this implies that the size of B is at least 4 because it has to have 4 different elements. But it has to be equal to 4 because every element of B must be in the set of F1, F2, F3, F of 4 because F is surjective. So therefore, the size of B has to be 4. Okay, so this kind of gives you some idea about how bijective functions or bijections can kind of give you information about the size of a set. In particular, if there's a bijection between two sets, then they have to have the same size. Okay. So let's actually prove that formally now. So this is proposition 7.5.1. So here we're only going to deal with finite sets for now, but next chapter we're going to talk about infinite sets. So let A and B be finite sets. Then the size of A equals the size of B if and only if there exists a bijection from A to B. Okay, so let's prove this. All right, so first of all, let's suppose that there's a bijection from A to B. So we're proving this direction, right? So the second statement implies the first. So suppose there exists a bijection F from A to B. So then any two elements of A map to different, so maybe I should say any two different elements of A map to different elements of B, because it's, by injectivity of F. So what I mean here is because it's injective, any two elements of A map to different elements of B. So therefore, B must have as many different elements in it as A does. So the size of B must be at least the size of A. Also, every element of B is the image of an element of A. So therefore, the number of elements in B must be at most the number in A. So therefore, if there's a bijection between A and B, then the size of B must be the same size, must be equal to the cardinality of A. For the other direction, suppose that size of A equals B. Let's say that it's equal to some n, where n is at least 0. So we can label the elements of A and B such that, A is little a1 up to little an, B is little b1 up to little bn, and now we define f to be a function from A to B such that f of ai equals bi for every I between 1 and n. Now, Perhaps I won't go into more detail than this, but it's pretty easy to see that this function is a bijection, right? So two different elements of A, let's say AI and AJ, will map to BI and BJ, which are two different elements of B. And clearly for every element of B, so if I look at BI from B, there's an element of A which maps to it, so which has, I mean, in other words, there's an element of A such that f of that element is BI, because you can just take AI. So that completes the proof. Okay, so let me just mention one more thing from the notes. So this is proposition 7.5.2. So it says that, so let A and B be finite sets such that the size of A equals the size of B, then a function f from A to B is injective or one-to-one. Maybe I'll use one-to-one. If and only if. So if I write this with IFF, this means if and only if f is onto. Okay, so the point is that actually, if you already know that the two sets have the same size, then actually being one-to-one is exactly the same thing as being onto. I think this is fairly evident, so I maybe won't give the proof right here. If you are interested in the proof, you can see the notes. But the point is, basically if you already know the sets have the same size, and I map everything in A to a different element of B, then you're going to have to map something to every element of B. And vice versa, if I take the elements of A and map them to the elements of B, if you map to every element of B and you know that A has the same size as B, then you must have mapped every 2 points to a different point of B. Okay, so the key things I want you to remember from this video are the definitions of one-to-one or injective, onto or one-to-one correspondence. So in other words, injective, surjective, and bijective functions. And secondly, you need to know how to show a function is or is not injective, surjective, or bijective. Okay? And if you're concerned that I didn't give you any examples where we were showing if things are bijective, well, that's because it's the same as showing something is injective and surjective. So if you know how to prove things are or are not injective, and you know how to prove that a function is surjective or not surjective, then you know how to prove that a function is or is not bijective. Okay, so I'll see you in the next video or in the next class. Bye-bye.